Hi, my name is Nurul Shakira binti Hassan. So today I'm going to present to you my project for ZCE111. Um, so my partner is Kelly Chong Hui and we decide to take the Stefan-Boltzmann constant as our topic for this project. So first of all, we need to know what is Stefan-Boltzmann constant, right? So Stefan-Boltzmann law states that the total radiant heat power emitted from a surface is proportional to the force power of its absolute temperature. So this statement formulated by Joseph Stefan in 1879. Then the same law was derived in 1884 by Austrian physicist Louis Boltzmann from thermodynamic consideration. So if E is the radiant heat energy emitted from a unit area in 1 second and T is the absolute temperature in Kelvin, then we get to know the formula is E is equal to sigma T to the power of 4. So sigma here represent the constant of proportionality called the Stefan-Boltzmann constant. And this constant has a z value after all the experiment have been did. So the value is 5.67037 exponent negative 8 watt per meter square per k to the power of 4. So after we all know this, we need to know the aim of this project. So the aim of this project is to integrate the thermal energy equation to obtain the equation of the total energy per unit area radiated by a black body, and then we need to program a code to determine the Stefan-Boltzmann constant, and we need to compare it with the actual value of the Stefan-Boltzmann constant. So we got to know the procedure of this project. So first, based on the equation, the a black body of unit area radiates electromagnetically an amount of thermal energy per second is equal to I omega d omega. So where the thermal energy equation is here. So by using integration method, we can get the formula of the total energy per unit area radiated by a black body. So this is the formula. So first of all, we need to import NumPy library and SciPy.integrate to the code. Then all the value of the constant needed in the function was stated. After we did that, the function of thermal energy was built. So we need to define the function of thermal energy. Then we set up the limit of the integral and we call out the result. Then after that, we need to determine the error. And the next step is our aim, which is we need to find the sigma by using the constant value stated above and the value of integral that we evaluate. Then lastly, we call out the result of the sigma by setting up to three significant figures as the question asks. Then by using the calculated sigma that we get, we compare the value with the actual value of the sigma. So this is an overview of the question. So now we need to discuss about the result. So for equation A, so this is the formula of the thermal energy, and we know that total energy formula is this. Then by taking h bar omega kBt equal to x, then we need to find the omega. So we already know the formula of omega is kBt over h bar times x, and we differentiate the omega and also the x. Then we insert the formula of omega and the omega that we already differentiate into the total energy formula, and we simplify all the operation here. Then finally we got the formula of the total energy per unit area radiated by a black body, same as the question. So this is proof. So now I'm going to share you the code of this project. So this is basically the view of the code of this project. So first, as we know, we need to import NumPy library and SciPy to integrate. This is an algorithm to integrate a function. So then we state all the constant needed in the sigma equation, sigma function. So first is h bar. H bar we get to know the Planck constant over 2 pi. Then we get the Boltzmann constant in SI unit and then the speed of light. So now we are creating the function of thermal energy that we get from the question. So this is the equation of the thermal energy, then we defined it. And now we set up the limit of integral. So based on the equation, based on the question, we know that the limit of the term of the um, thermal energy is 0 until the infinity. And now we call out the result based on the limit that we have set up. And now we determine the error. And we call out the result of the error. And now, um, after we already find all this, now we get to know the value of the sigma. And we insert the formula of the sigma, and we print the answer into three significant figure as the question asks. And now we run it. Yeah. Yes, so you can see here, we get the thermal energy is 7.0 and the error is also 7.0. And I think this is quite wrong. Wait, this is one. This one. Yeah. So now we can see the thermal energy is 7.0 and error is 2.019 exponent negative 8. And this is the value of the sigma, which is 6.10 exponent negative 8. So basically, I think this working is the best working because from the question, we just need to find the derivation of the thermal energy, and we get the evaluation of the integral, and next we need to find the sigma. And I think this is the best way for us to run the code of this project. Okay, now we already know the function, the sigma of us, calculated sigma, and now we need to compare it with the actual value. So, calculated value we get is 6.1 exponent negative 8, but the actual value is 5.67 exponent negative 8. So, we can see this have kind of different, which is not so far, but the value is 0.43 exponent negative 8. Um, so this happened maybe because of my code, or the heat absorbed from the heat radiate from the black body is not constant. And then lastly, we need to know the discussion or the conclusion of this project. So at the end of this project, we can conclude that from the Planck theory of thermal radiation, the total thermal energy per unit area radiated by a black body can be derived. And then Stefan-Boltzmann constant can be easily programmed by using the value of the integral. So I think that's all from me. Thank you for listening to my presentation, Doctor. And I think that's all from me. Thank you.